richness in North American bryophyte flora.
Hi, good morning. I really like thinking about kind of the big picture of kind of what's happening with bryophytes, sort of at the other end of the spectrum from what we've been kind of talking about so far this morning of kind of what's happening at that kind of really fine scale. So we're going to kind of zoom way out and talk about all of North America, at least North America, north of Mexico. Some of you notice about 20% of bryophytes in North America are endemic. And I used to think about, try to figure out why it is that that number is so low. So if you look at vascular plants, you see much higher endemism. And more recently, I've been trying to figure out why that number is so high. And so if you look at a lot of the population genetic studies and phylogeographic studies, it's really clear that spores are zipping around the world. There's a lot of long distance dispersal. And so regardless of whether it's interesting that endemism is low or it's interesting that endemism is high, it's interesting, right? And so we should try to figure out what's going on. And so that's kind of the premise of the talk today. And so probably one of the biggest and the best tool sets that we have, and I'm not going to talk about today, is population genetics and phylogeography. It's basically molecular tools where we can really kind of track down long distance dispersal and how it influences genetic structure across a continent. So there's a lot of population genetic studies and things like this where we're comparing closely related species, looking at how their genetic structure aligns or doesn't align with refugia and dispersal patterns and things like that. It's really important, not what we're talking about today. What I'm interested in is we've got these massive herbarium data sets, and those can probably give us some complementary information. So where the phylogeographic and population genetic studies are really good at giving us these little case studies, not little important case studies, we also need to think about kind of the big picture and what's going on. And we have the tool to do that in all these digitized collections. The data set that I'm going to be showing you after cleaning is in the range of 1 million specimens from across North America. So it's not a trivial data set. So the first thing that really jumps out at you and where I want to kind of start talking about this is if you compare endemic species, so that 20% that occur only in North America, we're going to compare those to the 80% that are native to North America, but also native to another continent. So it could be Asia or Asia and Europe, or it could be Australia or wherever. So the first thing that jumps out is if you look at the range size, and this is just if you map all the specimens and aggregate them into 100 kilometer by 100 kilometer grid cells, so pretty coarse. And you just look at the range size, they're massively different, endemics versus non-endemics. Twice the size in non-endemics. And that's true both if you break it down by latitude, so basically the non-endemics have sort of taller latitudinal ranges and much longer longitudinal ranges. And that's not entirely unexpected, just because if they're non-endemic, that means they probably live somewhere else, and so you might expect that they might have a bigger range here. But it's a striking pattern, and one that I think demands an explanation. So what I'm going to go through today are sort of 3 hypotheses to try and dig into what explains these major differences between non-endemic flora and the endemic flora. So hypothesis number 1 is that it could be that so if you just line up all bryophytes according to their dispersal and establishment ability, some are going to be good dispersers and establishers, others are going to be poor, and it could be that our special endemics are just crappy dispersers, right, and just kind of hanging out there. It could be a sort of more of an ecological filtering story, where again you line up all the bryophytes on a sort of spectrum of niche breadth, and it could be that the species with big ranges have broad ecological tolerances, and those are the non-endemics because they also experience those ranges on other continents. And then finally, it could be just an artifact of sort of geological history. So aerification in Western North America, for example, Pleistocene glaciation, things like that. And so Wolf Schofield in 1980, in a paper he wrote, came up with a hypothesis that makes a lot of sense, where it could be, so he was talking just broadly about the big difference between the Eastern North American and Western North American bryophyte floras. And so his thought was that in the Pleistocene, so basically you have these glaciers coming down, and you get two separate refugia, like a kind of humid refugium in the southeast, an arid refugium in the southwest. And then so following along with that line of thinking, then the non-endemics would be the sort of winners during the Pleistocene. So the endemics are kind of the losers. They got probably wiped out on other continents. And the winners were the non-endemics, and now they live on a bunch of continents. Because most of the species we share with Asia and Europe. So I'm just going to go through what evidence that I have in hand right now for these three hypotheses. And Brent just walked in, so I'm going to mention that this is not currently in a phylogenetic context. If dispersal was really important, we would expect that endemics should be disproportionately dioicous. And by dispersal, I mean dispersal and establishment. So it might be harder for dioicous species to establish because you need both sexes there to reproduce. You also might expect that endemics have larger spores. So there's some literature out there that suggests that spore size and range size may be correlated in bryophytes. But we can test that with data from the flora of North America and other places. And as it turns out, there's no difference here. So no difference in monoicous and dioicous between endemics and non-endemics. There is a spore size difference between endemics and non-endemics, with endemics having larger spores, but there's not really. That makes sense. So if you look at all endemics versus all non-endemics, you see a statistically different pattern. It's totally driven by thalloid liverworts. So it's just this kind of one group of endemics. And if you take those out of the analysis, the difference dissolves. So there's not a lot happening here so far, and I'm not going to present it, but there's some data also on asexual propagules that it's kind of a wash. If ecological filtering is important, we might expect that non-endemics are just, again, those species that have broader niche breadths, so which is going to correlate with larger ranges. And we might also expect that non-endemics perhaps have a different ecological niche from endemics. And so just as a kind of first pass to this, the way I'm approaching this is just doing a PCA of climate across, use the kind of standard bioclim variables across the continent. And then for each species all in the flora, just calculate the mean and standard deviation, so the niche mean, and using the standard deviation as a proxy for niche breadth. And this is broad scale. You know, so this is not fine scale, this is pre-course. But to see if these are offsetted. So sure enough, even when you control for range size, keeping in mind that non-endemics have larger ranges than endemics, they have broader climatic niches, which is kind of interesting. And they're also offset. So in addition to having a sort of broader standard deviation of climate, it's also displaced. And this is sort of a nuanced story, but the sort of like broad brush, single bullet point version is in general, endemics disproportionately occur in drier areas, and non-endemics disproportionately occur in cooler areas. And again, there's a lot of nuance there that we can talk about later if you like. And then this third hypothesis of Schofield's, it's basically kind of what we see in endemics versus non-endemics is more of a historical artifact. We can come up with some pretty clear expectations with that as well. So non-endemics, following this logic, should have more northern distributions because they'd be maybe kind of tracking the glaciers, living in those cooler environments. And then endemics should bear some kind of signal of these refugia. And so these scatter plots up here are the range centroids. So So each dot represents the sort of geographic average of a single species. So you were just take an average of basically all the specimens, and the XY coordinates, put a dot, then that's the sort of center of the range. So we got non-endemics in gray and endemics in red. So here we see a really, really striking difference between the non-endemics and the endemics. And these histograms are basically showing the same information, but just making a histogram of latitude versus longitude. So here in latitude, so in non-endemics in gray, you can see that the non-endemics are shifted towards the pole. So they're shifted and highly significantly northward relative to the non-endemics. And you can kind of make that out squinting at the scatter plot, if you like. And then what I think is even more interesting is this longitudinal histogram. So you see in the non-endemics, it's a unimodal distribution, kind of peaking in, so this is from west to east, so peaking in the deciduous forests of eastern North America. Whereas those endemics are bimodal. So you have these two really discrete groups of species. So in conclusion, like dispersal and establishment related traits, I don't think there's a big story there. It could be that there's some kind of nuances obviously happening, but I don't think that's really what's explaining these kind of range size differences between endemics and non-endemics. There is definitely some kind of a filtering signal, and I'm still kind of teasing this out. But it's very clear that the non-endemics do have broader ranges. And then this colder thing makes sense in the context. You can't really separate the ecological filtering from that geological history. It seems like those two things are kind of tied together. Because the endemics, where you get these two kind of groups in southern, southwestern, southeastern North America, those non-endemics are that kind of more northern, cooler belt. So right now, my working hypothesis is that even though the molecular data really clearly show us that there's a ton of long distance dispersal happening, but when we kind of zoom out and look at the flora as a whole, we really see, or at least I see, a strong impression of history. So we need to kind of, I think, balance our view, and the pendulum of kind of long distance dispersal and its important in bryophyte biogeography has sort of oscillated pretty wildly over the last few decades. And so I think this rivarium data really suggests that we need to continue to think about, and when we're designing our phylogeographic studies, think about cases where it could be a nice case of relictualism as opposed to always kind of looking for these nice cases of long distance dispersal. And my interpretation is that species that were pre-adapted to these cooler conditions were sort of the winners during the Pleistocene. And so they were the winners here, and they were also the winners in Europe and Asia. And so that's today what we call non-endemics. And then our endemics were kind of the losers during the Pleistocene, and very likely underwent extinction on other continents. We have no evidence for that, but it kind of makes sense. Okay, so to wrap it up, obviously I'm just kind of playing with numbers here. The real work of this project is generations and generations of collectors, and these days curators and digitizers and all the taxonomists, the people at the Flora North America project that kind of collate all these data. And then obviously the National Science Foundation for funding all these digitization